Good evening, everyone. Thank you for joining. This is one session in a series of Colorado ENP, or Emergency Number Professional Study sessions. Thank you to everyone who has helped put this together, including Connie, Jennifer Kirkland, who unfortunately can't be with us tonight because of another obligation, and Monica Million was also a big part of the planning of this. Tonight, we're going to be talking about 911 networks, and if that sounds like a big topic to cover in an hour and a half, it is. And I have no one to blame but myself because I'm the one who grouped the topics together for the study sessions. But we're going to get through it. We're going to be covering a number of different things. But first of all, for those of you who don't know me, my name is Daryl Branson. I am the Telecom Program Section Chief for the Colorado Public Utilities Commission. I was previously the 911 Program Manager for the state of Colorado under the Public Utilities Commission. And before that, I was the executive director of the Colorado 911 Resource Center, which is Connie's job now. Previous to that, I worked in several different positions in 911 centers across the country. I started off as a call taker and dispatcher in Springfield, Missouri. I was a shift supervisor at a newly consolidated PSAP in Waukesha, Wisconsin. And then I was a PSAP manager in San Juan County, New Mexico, before coming to Colorado. So I've kind of zigzagged across the country before coming here, but this is my forever home. So I'm glad to be here. As I said, we're going to be talking about 911 networks. I do want to give a shout out. This study session is kind of a group effort between the Colorado 911 Resource Center, the 911 Training Standards Institute, and the Colorado 911 program. We've gotten some really good instructors for some of the other sessions from the membership of the Training Standards Institute. I saw Michael Berry was on here earlier, who did I think he did the first session actually in this series. So glad to see him here as well. What we will be covering today, we're going to talk about basically four major areas. We're going to talk about enhanced 911 network design and architecture. We're going to talk about telephone network configurations. We're going to talk about what next generation 911 is, and we're going to talk about migration to next generation 911. Each of these topics could easily cover 2 days of classes. So we're giving you the hour and a half, 90-minute version of all four of these combined together. It's really covering at a high level what's in the study guide. If you don't have the study guide yet for the ENP exam, I highly recommend that you get a copy. It will help you understand what we're going to be talking about today. And includes a number of diagrams too, which can be useful that I did not put in the presentation today. And I'm going to be letting people in occasionally. There we go. So with that, let's get started on part one. We're going to talk about E911 network design and architecture. And within this part, we're going to be talking about enhanced 911 network terminology, network configuration, and transport facilities. So E911 network, I kind of got a little redundancy there, don't I? It's not E911 911 network terminology. It's E911 network terminology. Enhanced 911, or E911, which is also sometimes referred to as legacy 911 to contrast it with next generation 911. E911 is differentiated from basic 911, and this difference will be covered in other sections. Basically what I'm doing right now on this slide is just giving you some basic terminology. Again, I really can't stress enough that you really should get a copy of the study guide so that you can learn this terminology, because learning it just from this presentation is probably not going to be that effective, but we are going to be talking about what some of these things mean in a little more detail later. Another term to know is local access and transport area, or LATA. That is a specific geographic area within which a local TSP, or telecommunications service provider, may offer either local or long distance service. A telecommunications service provider, or TSP, is a company that operates a telecommunications network. So to give examples of this is everything from landline companies like CenturyLink, or the rural landline companies like Eastern Plains Telephone Company, or Nuclear Naturita Telephone Company, but also includes wireless companies the big national ones like AT&T and Verizon, as well as regional ones like Viero, or VoIP companies. So Vonage, Comcast, Magic Jack, all of those are different kinds of telecommunication service companies. So that category contains a wide range of different types. An end office. I've never heard it called a Class 5 office, but it says that in the study guide, so you should probably know that term as well. So an end office, also called a Class 5 office, is a facility operated by a local exchange carrier where different transport lines are connected between local users and the public switch telephone network. And we'll talk more later about what that means, because I know if you're not familiar with these terms, that can sound very nonsensical. But if you're looking back later at this presentation, that is the definition that is paraphrased from the study guide. A local exchange is a service area provided by an end office. A local exchange carrier is a telecommunication service provider that, I'm missing a word there, that provides physical connections to end users. A local loop is the transport facilities that connect the end office to the end user. An access tandem is a switching system that connects and distributes calls between end offices or to an inter-exchange carrier. Transport facilities are the physical medium that connects one point to another in the network. Examples of these include copper wire, fiber optic lines, microwave, satellite, and coaxial cable. We'll talk more about those later as well. A demarcation point is the physical points in the network where a call in a call flow where the responsibility for the network changes from one entity to another. And we'll talk a little bit about what that means later as well. Switching is the process of connecting a calling party to the called party without the use of dedicated transport facilities. So what they mean by dedicated transport facilities is if you have one line that directly connects point A to point B, you don't need a switching center. But if you have multiple lines coming out of if you have basically the way the phone system works, you don't have a dedicated line connecting you to everybody else in the world that you could potentially call. Instead, you go to a switching center, and then the switching center connects you to the lines that get you ultimately to your destination. Facilities is a broad term that refers to all physical equipment and lines and buildings used to house them, also referred to as physical plant. You'll see that in the study guide as well. Typically, we use the term facilities pretty broadly. It means the cable in the ground. It means the building that the switching center is housed in. It could even refer to everything within the 911 network, so like the alley database and so forth. All of those are facilities. So if we talk about what components there are to a E911 network, we have this diagram, which I put together. There are a number of different diagrams in the book. I tend not to like too many of the diagrams that are in the book. So in this case, I made my own. But we're just going to go through the different pieces here. So we'll start in the middle, which is a weird place to start, but I want to start there because it's really the hub of everything that we're seeing here. So the LEC network is a local exchange carrier network. So in Colorado, the biggest local exchange carrier is CenturyLink. They also happen to be the 911 system service provider, but they're playing two different roles there. As the local exchange carrier, providing landline service across the state. And how they do that is through a series of central offices, or I mentioned end offices. This is the thing that also goes by the term a Class 5 office. Those offices have the switching equipment in it that allows users at the end who have landline phones to make calls to the rest of the world. So now if we start down at the bottom, you have a user who makes a phone call. It goes up through these lines here, which are those local loops that connect the end user to the central office. The central office uses switching equipment to determine how to connect that call to the rest of the world. It goes up into the local exchange carrier's network, and within that network, that carrier has connections to all of the other carriers. They might have other carriers that serve as a go-between, which is called an inter-exchange carrier, which unfortunately has two different acronyms, IEC or IXC. But an inter-exchange carrier might also be an intermediary between the local exchange carrier and all of the other telecommunications service providers in the world. As a group, all of those other carriers in the world is frequently referred to as the PSTN, which stands for the Public Switched Telephone Network. So if you wanted to call somebody else that's in CenturyLink's network, you would make the phone call. The central office would send it up to the rest of the local exchange carrier's network. The local exchange carrier would say, hey, that user's one of ours. We don't have to send it out to the rest of the world. We can send it back down to whichever central office is within our network that serves that user. If it's in the same central office, let's say it's a local phone call, you're calling your dentist's office, and you both happen to be on CenturyLink phones, for instance, the call would go up to the central office, and it might not even leave the central office in that case. It can come right back down. But if it's in a different area, it's going to go all the way up to the local exchange carrier's network, and then they're going to send it to the correct central office for that user. If it is a different user, which frequently is the case these days, everybody has different carriers, especially because most people are making calls on mobile devices, the call is going to go up to the local exchange carrier. It's going to go out to the public switch telephone network and connect to that other carrier. All of this happens in the blink of an eye. So it's all very quick, but it has to go through a lot of different steps to get from point A to point B. Another thing that we will see frequently, especially in areas where there is either a large geographic area to cover or a large population to cover, you will see multiple remote central offices. So a remote central office, like a central office, is also considered an end office because it is serving users. But unlike a central office, it does not connect directly to the rest of the local exchange network. Instead, it has to connect to the central office first, which then will send it on to the local exchange carrier and then on to the public switch telephone network. A central office might sit alone where there are no remote central offices. It might have one remote central office. It might have two. It could have any number of them, usually no more than a small handful. But you do see any number of combinations with this where you have one or more remote central offices connecting to a central office. And we'll talk later about how that works. In enhanced 911, the call has to get to the 911 system service provider in order to be routed. So let's say somebody calls 911 down here in the central office service area, and they call 911. It's going to go to the central office. Central office says, hey, that's a 911 call. That has to go to the system service provider. It goes up to the local exchange carrier network. The local exchange carrier network connects it to a 911 entry point. A 911 entry point, in our case, and in most legacy 911 cases, is going to be a selective router. So it goes to a selective router. Selective router looks at the phone number, compares it to a table, which has all of the phone numbers that are possible in that network and which public safety answering point the call has to be routed to. And it's going to say, okay, you need to route that to XYZ PSAP. In this case, there's a PSAP that is in that service area. And in most cases, if there's a PSAP that's in that service area, not always, but in most cases, if there's a PSAP that's in that service area, that's going to be the correct PSAP to send that call to. So it seems nonsensical for the call to have to go all the way up here in order to be routed all the way back down here. But that's what happens in most cases. But the reason for that is because it gives us a lot more flexibility. We can have PSAPs anywhere and have it routed to the right PSAP. It doesn't have to be in the same central office service area. So for example, I just arbitrarily put a PSAP here in this service area and a PSAP here in this service area. But let's say somebody calls 911 from this service area. It's going to go to this remote central office. It's going to be sent to this central office. And then it's going to go up to the 911 system service provider. And based on that table, the 911 system service provider is going to know, okay, that call needs to go to a PSAP that isn't in this same remote central office, and it's going to route it back to that appropriate PSAP. It might be this one, in which case it'll route it down here, even though the call started on the right here. Or it could be this one, in which case it's going to route it through the central office to this other remote central office and down to this PSAP. Or it could be in a different local exchange area entirely. And we have any number of combinations of these in Colorado and in other parts of the country. And that's what Enhanced 911 does, in addition to providing the location information because of the ALI database. It allows for flexibility on where calls are routed. In basic 911, before Enhanced 911 was a thing and before you had selective routers, the calls could only be routed to one place. So if somebody called 911 in this service area, it would go up to the central office. Central office had one place it could route it, which is this PSAP. And so it limited basic 911. We normally think about the change from basic 911 to Enhanced 911 to mostly be about location information, and that was a huge part of it. But really, the reason why it is called Enhanced is not because of the location information. It's because of the ability to route calls to anywhere you want within the network. And by the way, if anybody has a question, there's no need to wait for the end. Go ahead and raise your hand or just break in and ask it so that we don't have to wait till the end, because like I said, there's a lot of information. I don't want your question to get lost in the shuffle. One of the other terms I talked about earlier is a local access and transport area. This is kind of antiquated, at least in Colorado. There are still parts of the country where this matters, but a local access and transport area is a larger area. So you can think of a local exchange area being a small area, usually a county or maybe part of a county, where there is a central office and one or more remote central offices that are serving that area. But a LATA is a larger area that basically used to define what a long distance area was. So if you had to call somebody from one local exchange area in this 658 LATA to another local exchange area in that LATA, that would be an intra-LATA, intra meaning within, an intra-LATA long distance charge that you would be charged. If you were to call from this LATA to a local exchange area in a neighboring LATA or in the LATA on the other side of the country, that would be an inter-LATA long distance charge. The reason why it mattered for 911 is because the selective routers were originally built within each LATA, and you could not transfer calls from one selective router to another. So let's say somebody calls here to report an issue with their neighbor or their loved one in the next town who happens to live in the next LATA. You wouldn't be able to transfer that 911 call across that LATA boundary. That has since been alleviated in Colorado. You can now transfer calls anywhere from one point to another within the 911 network in Colorado. So this is not really an issue anymore here, but the term is in the book, so it might be on the test. So local access and transport area, that's what they're talking about. Talk a little bit about transport facilities. So there are a number of different ways that not just 911 calls, but any kind of phone call can be transmitted across a network. Starting with copper wire. This is being slowly retired, but there is still a lot of copper wire being used in today's telephone networks, particularly in large networks and in rural areas like you're going to see in Colorado. The economics of replacing all of this copper wire quickly with fiber is extremely expensive. So it's being done a little at a time. So you still see a lot of copper wire in Colorado. The common telephone wire is formed from a pair of copper wires twisted together. So this is sometimes referred to as a twisted pair. This is talked about in the book as well. And copper can be used to transmit analog or digital signals. We think of it as older technology, so we might think of it as an analog signal only, but it actually can be used to transmit digital signals. I remember from the old days with my 2400 baud modem that you can transmit digital signals across copper wire. but it is no longer the preferred method of transmitting telephone communication. Everything is rapidly changing to fiber optics. These are extremely thin filaments of glass. You don't think of glass as being flexible, but when you stretch it out like this, it does actually become flexible. And it is extremely thin. It is the width of a human hair. And it is used to transmit pulses of light. This medium is slowly replacing copper because it offers very high bandwidth at low costs and can be transmitted over long distances. Fiber is also not subject to electromagnetic interference the way copper is, and all transmissions over fiber are digital, but they can be converted back to analog at the endpoints. Another medium that is not used as much, but still is an important part of a lot of telephone networks is microwave. These are directional radio that can be used to send and receive transmissions at a range of about 30 miles or longer if a repeater is used. Microwave is susceptible to fade or interference due to weather conditions, but it's used in a lot of places where it is just not cost effective to lay down fiber or bury fiber, and can sometimes be the only feasible way to connect 2 points in the network due to terrain. So where we tend to see microwave in the 911 network in Colorado, there's not very much of it, but there is some of it. We see it in the very mountainous areas of the state, and we see it in the wide open plains part of the state. The mountain areas, it's there because it is just not economically feasible in some cases to use fiber because you have to lay that over mountain passes. And in the rural areas of the state, where the plains part of the state, it's not feasible because there's just not that many people there to serve. And so they have to get this over a long distance without a lot of reasons to stop the signal in between. So it's cheaper to use microwave in those areas than it is to build fiber. Satellite is not used a whole lot in our network, but it is used in a lot of other telecommunications networks, especially wireless networks. The study guide is a little outdated on this topic. It says that it talks about geosynchronous satellites pretty much exclusively. So for the test purposes, that's what you need to know about are geosynchronous satellites. These exist at a really high altitude. The satellites are at 22,300 miles. What geosynchronous means is that the orbit of the satellite is the same as the rotation of the Earth. So even though it's going faster around a much larger circle because it's that high up around the Earth. It's at 22,300 miles. So no matter what time of day it is, if you were able to find that satellite through a telescope, for instance, that satellite would always be there. It doesn't move in the sky. However, one thing that's not mentioned very much in the text is that there is now a much bigger increase of low Earth orbit satellites. These are much closer to the ground at 186 miles to 1,200 miles. They are not geosynchronous, meaning that they don't stay in one place in the sky, but they make up for this fact by having a large number of the satellites so that when line of sight is lost to one, the signal can switch to a different satellite. Like microwaves, satellites are susceptible to interference from weather and also atmospheric conditions. This is one of the reasons why they're not typically used in mission critical communications unless it's as a backup. There has been talking about using satellite as backup communications in Colorado's 911 network in the past, and that may still happen at some point in the future, but it hasn't happened yet. Coaxial cable. This is your cable TV cable. So if you've ever seen a cable TV cable, this is what the inside of one of those looks like. It's a copper wire, just like the twisted pair copper wire, but it's bundled and shielded from electromagnetic interference. And because of that, it has a higher bandwidth than the traditional twisted copper. It is not widely used to provide telephone service, but some of it exists in today's networks. And you can run VoIP service over it, obviously, because that's how Comcast provides their VoIP service. It has some of the benefit of fiber, meaning that it's higher bandwidth than traditional copper, and it's shielded from electromagnetic interference. but it can also carry analog signals without having to convert them at the endpoints to analog, like fiber cannot. However, it is more expensive than fiber and does not have as high of a bandwidth, which is why it's not used very widely in the network. So that was part one. We went through that very quickly. If anybody has any questions, I can pause now or we can keep going. Okay, we'll keep going then. Part two, we're going to talk about network configuration. Within this section, we're going to talk about switching configurations, selective routers, and E911 selective routers. We're going to talk about some of the features of E911 selective routers, signaling systems, and transmission systems. And by transmission systems, we're not talking about a car transmission. So switching configurations, this is pretty much what I was showing earlier, that we have different configurations of how landline networks can connect to end users, usually through the use of a central office and one or more, sometimes none, but sometimes one or more remote central offices. This becomes really important when you start thinking about how outages can happen. So an outage can happen really anywhere in this design, right? An outage can happen in the local loop, which may or may not impact a PSAP, but will impact some of the end users who are relying on that local loop to connect to the central office. It can it can happen at a remote central office. If that remote central office has a PSAP, then it's going to affect that PSAP. If it does not have a PSAP, then it's not going to affect that PSAP, but that PSAP will not be able to get calls from users that were in that remote central office. And it can happen between any of these points. So it can be a cut between these two, or it can be between the central office and the rest of the local exchange carrier network. But what I was talking about earlier with how switching with switching configurations, this is what we were talking about. E911 selective router, another term that you will see for that and may show up on the test is a 911 tandem. That's kind of an older term, but some people who've been around a long time in the 911 industry still use it. So when they say a tandem, it's the same thing as an E911 selective router. The reason why an E911 selective router, or why E911 no longer works when a central office becomes isolated, is because E911 requires that all calls reach that selective router. So that's what I was talking about earlier. Let me go back to that diagram real quick. Did I pass it? I did. It's this one right here. So as I mentioned earlier, when you call 911 in an E911 system, this call has to get all the way up to the E911 selective router in order to be routed to the appropriate PSAP, whether it's in the same area or not. And that's why 911 goes down if there is a cut between the central office and the rest of the local exchange carrier network, or between the local exchange carrier network and the basic emergency service or 911 system service provider. Back to that. The selective router uses a routing table, as I mentioned earlier, that matches the phone number from the call to the PSAP that is assigned to take 911 calls from that area or from that phone number. The call is then routed to the correct PSAP. Claire says, if you can relate any of this to something local, that would make it easier for me to understand. Yes, I can do that. I can make up examples, but I don't have a network map in front of me, so I can't tell you exactly where the central offices and remote central offices are, but I can make something up. So let's say, for example, we'll use Boulder County as an example. So let's say the city of Boulder has a central office and Longmont has a remote central office that connects to that central office. That may actually be the case. I would have to look at a network map to tell you if that's the case. But for the purposes of an example, let's do that. So let's say that there is a fiber cut between the central office in Boulder and the rest of the CenturyLink network. What that means is that all three of these central offices become isolated. They cannot call out anymore. They can't call out of this local exchange area. That means that no calls from any of these central offices will be able to get to the E911 selective router, which means 911 goes down for every PSAP that's within that local exchange area. And that's why redundancy, by the way, is important. If there's more than one connection, then one fiber cut won't cause an isolation. If there is a fiber cut between, let's say this is Longmont, between Longmont and the central office in Boulder, Boulder is going to chug along just fine. People in the Boulder central office and any other remote central office that's connected to it will still be able to make 911 calls. Anybody served by the Longmont central office, or remote central office, I should say, won't be able to make 911 calls because calls get from here to the rest of the network. I hope that helps. And if it doesn't, let me know.
That's great. Thank you, Daryl.
You're welcome. So what this does, because it's routing calls to a PSAP based on the phone number at the selective router, this allows us, as I said earlier, to have a lot of flexibility on where we want to have PSAPs. You can have multiple PSAPs that serve the same central office service area. As an example, we have Boulder County Sheriff's Office has a PSAP and Boulder County Police Department has a PSAP. Both of those PSAPs will be served by the same central office because they're so close together. And the 911 network knows which PSAP to send it to, not based on which central office is serving it, because they're both served by the same central office, but based on that tabular routing table that is used at the E911 selective router to determine which PSAP to send that call to. It also allows you to have a PSAP in a completely different area from where the 911 call is taken. An example of that in Colorado is, a really good example of that is San Luis Valley. San Luis Valley is 6 huge counties geographically that are all served by one PSAP. So if somebody calls 911 in Rio Grande County, it doesn't go to a PSAP in the remote central office or central office that serves Rio Grande County. The 911 network knows that that call is answered in Alamosa, which is quite a ways away from where you might be in Rio Grande County making that phone call. And the way that it knows that is because the call is going all the way up to a E911 selective router, and the E911 selective router is using that routing table to figure out where that call has to go. Selective router versus selective routing. This is really tricky if you're talking about terminology, if this terminology comes up on your ENP exam. These are two different things, but they sound very similar. An E911 selective router is a specific type of equipment used to route 911 calls to an appropriate PSAP, and it really only applies to an E911 network. You can have legacy selective routers in a transitional network, but it is still an E911 component. And it uses a tabular database that matches phone numbers, or in some cases PNEs, which we'll talk about in another section, with emergency service zones, and those emergency service zones are assigned to a PSAP. Selective routing is a more generic term, and it refers to any method used to determine how to route 911 calls to an appropriate PSAP based on a phone number or caller's location. This means that selective routing happens in NextGen 911 too, but E911 selective routing does not happen in Next Generation 911 because Next Generation 911 does not use tabular databases to route 911 calls. So there is a difference between these two terms, even though they're very similar. So I just wanted to point that out because that might trip you up on the test if either of those terms come up. E911 selective routers have a set of basic features that you can find in almost every E911 system across the country. The basic set of features starts with selective transfer. It's the ability to transfer a call to police, fire, or EMS agency based on emergency service zones associated with the call. To my knowledge, this isn't really used in Colorado because we have mostly consolidated centers. But it used to be that once you got the call, and not only would we have consolidated centers, that almost every center is dispatching the calls that it receives. But we used to have the ability to transfer calls from a PSAP, which is answering a call, to a dispatch center, which is dispatching the call based on whether it's police, fire, EMS. That's probably still used in a number of places in the country, but to my knowledge, it's not used much in Colorado. Call conferencing, that seems like, well, of course we have call conferencing, but that is a feature of an E911 selective router. That's basically your three-way calling, your call or your conference transfer. This is important if you are doing a warm handoff of a call to another PSAP, or if you are bringing somebody in on the call, like a language line, a translator, for instance. That's what this is referring to. One-button transfers. A lot of times that's handled in the call handling equipment itself, not through the E911 selective router, but it is something that can be set up through an E911 selective router. Alternate routing. Again, we think of that as a very basic feature, but basic 911 did not have alternate routing, where if every line at the PSAP is busy, the 911 network knows that, okay, every line of that PSAP's busy, I'm going to have to send it to another PSAP. And we have a table that goes 1 or 2 or 3 levels deep that we know that this call has to go to this other PSAP. This can be done automatically or upon request. In E911 systems, there used to be a switch in most of the 911 centers called a make busy switch. Sometimes we have another switch that kind of replicates that feature in next generation 911 systems, but it's just a physical switch in the 911 center that you can flip that tells the 911 network that PSAP is no longer available, and it will automatically start routing calls to an alternate PSAP. Default routing is something that's also built into 911 network in the E911 networks, which is routing a call to a default PSAP when selective routing is unavailable. To my knowledge, in Colorado, the entire time I've been here, I don't believe we've ever had a selective router outage. And I'm knocking on wood. We don't ever want to have a selective router outage. But if there were a selective router outage, then default routing would basically say, okay, I don't know which PSAP to send this to, but for all calls from this central office, we're going to send them all to this PSAP. So basically, it's going to route calls based on which central office received that call. Signaling. This is getting into some really propeller head stuff, but they spend a lot of time on it in the study guide. So I would suggest knowing at least a little bit about signaling, but we're getting into the real nuts and bolts of how telecommunications networks work. Originally, phone lines had no way of carrying any data in addition to the voice of the caller. This meant that the phone number that the call was coming from was not available to the network, and without a phone number, selective routing couldn't be performed. So signaling is very important to the evolution of 911, because without signaling, there is no way for E911 to work. It would have no phone number to know where the call was coming from, to match that on a database, a tabular database, to determine where to route the call. And so this is necessary for a number of reasons. It was necessary just for regular phone calls to automate call setup. If you watch really old TV shows like the Andy Griffith Show, you see people pick up the receiver and they talk to an actual operator who they would then say, hey, I'm trying to call so-and-so, and the operator would connect them. That's how it had to happen before there was any way of transmitting even the phone number that you were trying to dial to. So all of this signaling was a necessary component for automating how telecommunications networks work, as well as for making E911 possible. So selective routing of calls, as I said, can't be accomplished unless there is some data attached to, or transmitted separately to indicate where the call came from, such as the phone number. And a number of different signaling technologies were invented over time to make this happen. There are two basic types of signaling. One is out of band, which means that it is not done on the same line as the phone call. What happens instead is the signaling is done over a separate channel, which could be on the same physical line, but it's not being transmitted along the same path as the voice call, or it could be done over a separate line entirely. And this is called control channel signaling. There's two types of that. One is SS7, which is short for signaling system number 7. I don't know anything about signaling systems 1 through 6 or 8 and then into infinity, so don't ask me about it. But signaling system 7 is what is still used quite extensively in modern telephone networks. And it's a type of telephone connection line that allows for a limited amount of data to be carried along with the phone call. Another type that until very recently was used widely in the 911 network here in Colorado, and is still used in enhanced 911 networks across the country, is centralized automatic message accounting, or CAMA. And that was originally developed to help track long distance phone calls, because it allows, in addition to the voice, it allows the line to carry a certain amount of data, including the originating phone call, which is important for billing purposes for long distance, how long the call lasted, which is important also for billing. So it all came down to billing, but it also had the ability to deliver the phone call, which made E911 calls possible over those types of lines. And then you have in-band signaling, and there are two types of those. I'm not really going to go over the distinction, because the text doesn't really go over the distinction very much between these two types of in-band signaling. But there's multi-frequency signaling and dual tone multi-frequency signaling. Some of you on the call may be too young to have ever heard this, but if you ever picked up a touch tone phone and started pushing the buttons, then you heard sounds like this. Hopefully this comes through on the broadcast. Oops. I have to actually, there we go. Who's hearing that? You either hear silence or hearing these tones. Somebody give me a thumbs up if you hear any tones. I'm not seeing any thumbs up.
There was just barely a squeak of a tone, but no firm tones.
Well, that's unfortunate. Luckily, that's the only sound effect I have in this presentation. But some of you probably know what these sound like. If you ever picked up a touch tone phone and dialed the numbers, you could hear, and dialed is an old term too. If you pushed the buttons on the touch tone phone, you would hear a very strange sound, and the tone would be different for each button. That's actually combining two different tones to tell you exactly which number is being pressed. Those tones then could be decoded on the other end, and that allowed the network to know what numbers were being dialed. Other types of numeric data could be transmitted that way across the network, encoded into those tones on one end and decoded on the other, which allowed for a number of different scenarios where the data was being transmitted across the network. And there we go. And another thing that the text talks about is the difference between analog and digital transmission. Analog transmissions are ones that are variable in amplitude and or frequency. And really, that's a complicated way of saying that it works just like sound waves do. So whenever you're talking, you hear me talking right now, my voice is vibrating the air, and it's changing the frequency, which changes the tone or pitch, and the amplitude, which changes the volume of what I'm saying. And all sound really breaks down into amplitude and frequency. An analog transmission is one that takes that amplitude and frequency and finds a way to transmit it across another medium. So with copper wires, it's actually vibrating that copper wire through an electrical signal that is mimicking that amplitude and frequency that then can go into a speaker on the other end, and you hear the sound that just sounds like my voice coming out of that speaker. And it's amplitude modulation and frequency modulation. By the way, that's where AM radio and FM radio get their names. If you ever wondered why it's called AM and FM radio, it's because one uses amplitude modulation to transmit the signal, and one uses frequency modulation. This modulation, as I said, mimics how the human voice works. And in the same way, analog transmission over copper wire is doing the same thing, but it's doing it over a longer distance. It works well for the human voice, but it's limited in the amount of other types of information that it can transmit, which is why copper is not really used that extensively anymore. Digital transmissions are ones that have only two modes, on and off. So instead of varying the amplitude and frequency, the frequency is constant and the amplitude is either high or low, representing on or off. While this seems like it would reduce the amount of information that it can be transmitted, it actually allows for much more information to be packed into a short duration, essentially compressing the data. So this on or off signal means that the data can be translated into 2 digits, ones and zeros, which is also known as binary code, and which is the code that all modern computer hardware operates on. Just as an example, a visual example of what this looks like, an analog signal, you can see that it varies in amplitude. This diagram doesn't really show it varying in frequency, but varying in frequency would mean that the waves get closer together. But a digital signal is the same amplitude in just 2 different modes. It's either high or low, and the frequency is the same. You see these breaks in here, but it's actually, if you translated this is a 1. There's a break here, so that's a 0, 1, 1. So if you were to translate this would be 1, 0, 1, 1, 1, 1, 0, 1, 0, 0, 1. So that's how it translates a digital signal into ones and zeros, which are then translated into other types of data. Which brings us to packet digital transmission. Packet technology is a type of digital transmission where the groups of ones and zeros that I were just talking about get separated into packets or groupings of data. So you have data that's broken up into packets, and we'll just use an example. You want to send a friend of yours a funny meme that you found on Facebook. So you text it to them. That is being sent as data across the wireless cellular network that you use. The data, that picture is broken up into a series of packets. I don't know how many packets. Could be a couple dozen, could be 100, could be 1,000. Each of those packets has a set of ones and zeros in it that are then sent across the network. And then on the other end of the network, those packets are reassembled into that picture that you just sent your friend. So the data is broken up into packets and transmitted across the network and then reassembled on the other end. And this is the basic foundation of how the internet works. So all internet communication is done through packet technology. You hearing me right now, because we're transmitting this presentation over the internet, my voice is actually being broken up into data packets, transmitted across the internet, and reassembled on the other end and turned into a sound stream that you're hearing over the speakers on your computer. So that was a lot of really nerdy technical stuff. The book spends a lot of time on it, though, which is why I spend a lot of time on it. Does anybody have any questions about transmission mediums or transmission types, with the analog versus digital versus packet? Anything along those lines? All right. So now we're going to talk about next generation 911. This is really high level. I believe other sessions will go into more detail on some of these components of it. But we're going to talk about what next gen 911 is, and we're going to go over some of the terminology involved in next generation 911. So at a very high level of what next gen 911 is, as we've discussed, communications technology had to evolve significantly just to allow for the implementation of E911, but commercial technology has evolved a lot faster than 911 networks have. By using internet protocol, commercially available communications technology can handle any type of data imaginable. So in an enhanced 911 system or in a transitional 911 system like the one we have here in Colorado, you can still not send over that 911 network pictures, video, text, vehicle data, building plans, medical data, or any other type of data other than voice. And every one of us can do that right now on our cell phones. So our cell phones are much more technologically capable than our 911 network. So in the meantime, E911 systems are still capable of delivering only two things: the caller's voice and the caller's phone number. That phone number is then used to get the location information via a completely separate channel. So you're not even getting the alley information, the location information that shows up when somebody calls 911. You're not even getting that over the 911 network. That's done over a separate circuit. So the 911 system is very limited compared to what is available in commercial technologies. So for this reason, NINA created a standard for an IP-based 911 network that's capable of handling any type of data desired. The primary standard created by NINA for this purpose, and this is mentioned in the text, which is why I mention it here, is NINA-STA, which is short for standard, -010, which is the NINA i3 standard for next generation 911. A lot of times it's just called the i3 standard. So if you hear somebody say the i3 standard, they're talking about the standard for next generation 911 systems. You are not required to know everything there is to know about next gen 911 for the ENP exam, which is good because we wouldn't be able to cover it in these sessions, and you wouldn't be able to put it in a book that is 188 pages thick like the study guide is. But we will go over some of the terminology that's specific to next gen 911 that may be on the test. So to start, we're going to talk about IP networking. As discussed earlier, Internet Protocol, which is usually shortened to IP, operates by taking digital transmissions of ones and zeros and breaking them into packets and sending them to a destination across a network to be reassembled. This method is called Transmission Control Protocol / Internet Protocol, or TCP/IP. It's usually referred to just as IP, but if you see TCP/IP on the test, that's the same thing. TCP/IP is the protocol that allows the internet to work. And it's also the protocol that allows next-gen 911 to work because it's using the same protocol as the internet. Conversion of 911 systems to IP-based networks is necessary in order to better accommodate existing voice technology, such as VoIP and wireless phone services, but it's also necessary to allow the transmission of other types of data and to better serve the public. So I talked about the other things. We think about the bells and whistles like text, pictures, and video, but it can also be things that are really practical to the first responders, like building plans, medical information, any other type of data that could potentially be useful to the first responders could eventually be transmitted over a next-gen 911 network. Another term that you're going to need to know is an ESINet or ESINet. There's a long-standing debate as to how it's pronounced, if you pronounce it ESINet or if you can say ESINet. I've always said ESINet, but both pronunciations are appropriate. That is short for an Emergency Services IP network. It is an IP-based network created specifically to handle emergency services communication that replaces the analog 911 network, which, as I said earlier, is sometimes referred to as legacy networks, which would include both basic 911 and E911 networks. ESINets can be really small. You can have one ESINet serving one PSAP, or they can be as large as a region or a state, or theoretically even a nation or the whole planet. They can be a single network, or they can be a combination of networks owned by different providers and interconnected with each other. This arrangement would be called a network of networks, or an internetwork. An ESINet is not the same thing as next-gen 911. It is the network itself, but not the services that operate on it that would make the network an NG911 system. So you can think of an ESINet as the platform that you then have to put all of the other components and features on to turn it into a next-gen 911 system. It is an absolutely necessary part of a next-gen 911 system, but an ESINet by itself is not a next-gen 911 system. And what we have in Colorado, we have a statewide ESINet. Whether or not you would consider us a next-gen 911 system kind of gets into an area of semantics, because we have some of the components from the i3 standard, but we don't have all of the components from the i3 standard. So we're kind of in a transitional stage. But before we ever get to next-gen 911, the ESINet had to come first. And that's where we are right now. NGCS stands for Next Generation 911 Core Services. So if we think of the EZNet as the platform, NGCS are all of the things that go on that platform that turn that network into a Next Gen 911 network. There are a number of required services. There's a number of other services that can be added onto a 911 network that's part of Next Gen 911, but the required services are the ones that are listed here. Emergency Services Routing Proxies, or ESRP, Emergency Call Routing Function, ECRF, which are both of those are components that are necessary for routing 911 calls on a Next Gen 911 system. That's what's being done instead of those tabular databases that I talked about earlier in an E911 network. Location Validation Function, or LVF, Border Control Function, or BCF. Border control functions are used to make sure that there is no unauthorized access to the network. It exists on either end of the network to make sure that, and sometimes in middle places in the network as well, you can think of it as the security guard that's making sure that only the data that's supposed to go through the network can go through the network. Policy Store. I don't know if they're going to talk further about policy stores in other parts of in other sessions of the study sessions, but essentially that's where you can tell the network specific routing instructions, like say, I want 911 calls from this neighborhood to be routed to PSAP A during business hours, but outside of business hours, I want them routed to PSAP B. It gives us a lot more flexibility in how calls are routed than in an E911 network. Logging services, this includes the types of logging that you're used to, so call recording and things like that, but it's also logging every action that takes place on the network. So not only are you logging what's happening in the PSAP, but you're also logging every step of a call along its route along the network. And there are a few other basic IP components that are not mentioned here, but they're necessary components of any IP network, not just Next Gen 911 networks. We'll talk about at least one of those here in a little bit. But together, these functions are referred to as Next Generation 911 Core Services, or NGCS. So if you see that term, that's what this is referring to. It's all of these components that turn an EZNet into a Next Generation 911 system. They are not part of the EZNet. They're considered separate from the EZNet, but the two things need to be together in order to operate. So an EZNet by itself is not Next Generation 911. NGCS by itself is not Next Generation 911, but you put the two together and you have a Next Generation 911 network. Another term that you will see in the text is functional elements, sometimes abbreviated to FEs, or just an FE. These are basic functions and components of a Next Generation 911 system. Some of these are necessary core components. So for instance, every one of these bullet points on this page that we just went over is an FE. So there's an FE that's called an Emergency Services Routing Proxy. There's an FE that is a border control function. So any piece of the Next Gen 911 network is a separate functional element. Some of them are necessary and some of them are optional. But dividing the parts of the Next Gen 911 network into different functional elements is a way of making the system more adaptable and flexible. And it also means that different components can be changed out without replacing entire systems. And it also allows potentially different vendors to provide different parts of the system more easily. So you don't have to have one company that's in charge of every piece of the network. You can have different companies providing the EZNet, for example, is an FE itself. And each one of these is a different FE. Different companies could be providing these different parts separately. So it gives a lot more flexibility in how we design and how we procure our networks. Another term you will see is an NG911 PSAP. This is also sometimes just called an I3 PSAP. The network itself isn't the only thing that has to change in order for Next Generation 911 to be implemented. The PSAP itself has to upgrade its equipment to be able to receive calls in IP format as well as the I3 format. So there's a specific format for calls. We'll talk a little bit later about what some of that formatting is about. But the equipment at the PSAP has to be able to receive calls and handle calls in that I3 format. So if a PSAP has hardware and systems that are capable of handling calls in I3 format, then it is an I3 PSAP. One of those types of formats is EIDO. So this stands for Emergency Incident Data Object, which is a set of data that can be shared between, among authorized entities and systems in a next-gen 911 system. You can think of this as a combination of all the call data that's associated with that call. So all the things that you get now from the alley data, which is, if it's a landline call, for instance, you would get the caller's name. You don't always get the caller's name with other types of phone calls, but the caller's name, the phone number, the location, but also other things like the duration of the call and any data that has been added to the call at the PSAP. So this is your call notes from your CAD system, what units were dispatched on the call, when it was dispatched, all of those types of details are combined into one set of data called the Emergency Incident Data Object. This allows data related to an incident to be transferred from to another PSAP, or you can share it with multiple PSAPs, or, and this is the really neat thing that I hope to see someday before I retire from next generation 911 systems, is to share this data with other entities that are authorized to receive the data. So examples of this is you might get a call from somebody who's just been in an automobile crash. So you get the call data that comes with that call, but then you're adding to that EIDO with all of the data that you are entering in the CAD system, every unit that you dispatch on that call, all of the automatic crash notification data that came in behind the scenes could be included in that EIDO as well. You need certain information from that to dispatch the call, but that EIDO could also be shared with the EMS personnel so that they know how fast the vehicle was going, they know whether the vehicle flipped, they know whether everybody in the vehicle was seat belted in, because all of that data was included in the automatic crash notification data stream that was then included in the EIDO. That would help them serve that patient better. It's not information that you necessarily need to know at the PSAP. You might need to know some of it, but they would get a lot more information that would help them serve that patient. When they get to the ER might need different data from that EIDO. Law enforcement might need even more data from that EIDO for their crash investigation. So that's one example of how an EIDO can be used to share data, not just with another PSAP, but with entities potentially outside of the PSAP environment. Spatial interface, which is abbreviated as SI, is an interface that allows functional elements within an NG911 system to access GIS data or geographic data. So this is necessary because NG911 calls are routed based on where the call plots in the GIS data, not based on a table that matches a phone number with PSAPs like an E911. So if a call comes in with a latitude and longitude in a next-gen 911 system, it's taking that latitude and longitude and it's comparing it to a GIS data file to determine which PSAP to route that call to. The interface between the different components of the NG911 system that allow it to compare that data to the GIS, that lat and long to the GIS data, that interface is called the spatial interface. The spatial interface also distributes copies of the GIS data across the NG911 network. So in E911, call routing happens at the E911 selective router. It has to go to that selective router to get routed. And there's only 3 of them in Colorado. There's 3 sets of them in Colorado. In a next-gen 911 network, the calls don't have to go to a selective router. They go to any one of a number of routers that are on the network. And each one of those routers will have a copy of the GIS data for the whole state. The spatial interface is the functional element that transmits those copies across the state and makes sure that they match so that every router in the state is using the same GIS data. Forest guide. This is an important one to note that this doesn't exist yet, but it's an important part of the overall Next-Gen 911 framework that was created by NINA. So as I mentioned earlier, EZNets can be interconnected to function as if they were one larger network. So let's just give an example of if Colorado gets its EZNet fully upgraded to a full Next-Gen 911 network, and let's say Nebraska also has a fully functional I3 Next-Gen 911 network. Those two networks can connect to each other to transfer calls back and forth. But in order for that to work, there has to be an authoritative source that keeps track of and provides information upon request about the service boundaries of those two ESI nets. If a 911 call has to be transferred or routed from one ESI net to another, then it has to query what's called a forest guide, which then will find out which ESI net should receive it next. So ultimately, the vision is that there might be a few dozen EZNets, maybe a few hundred, it doesn't really matter how many, across the entire country. Once the entire country is covered in EZNets, you would be able to transfer a call anywhere from if you had let's say you get a call in Colorado, but they're calling because they found out that a relative of theirs in Florida is having a heart attack. You want to transfer that call to Florida, you would be able to do it. And the forest guide is the entity or the functional element that tells the network how to route that call to the other EZNet. Claire, go ahead.
Who creates a forest guide?
That is the million-dollar question. So that's why it doesn't exist yet, is because nobody has taken ownership for creating that. Potentially, it could be a federal agency that does that. Maybe for example, the National Telecommunications and Information Administration, or NTIA, that has been talked about as maybe being the entity that would create the forest guide. It might be a nonprofit created by organizations like NINA and APCO that would do that. But that's the reason why it doesn't exist yet, is because nobody has taken ownership has said, yes, we want to be the ones to create this functional element that will help guide 911 call routing for the entire country. Because as you can imagine, that's not an easy thing to do. And there's also a lot of liability involved if they do it wrong. So good question. DNS. So I mentioned earlier that there are some components that are necessary on Next Generation 911 that are not unique to Next Gen 911. DNS is one of them. It stands for Domain Name Service. This is a standard function on all IP-based networks, but it's also present in Next Gen 911, so it's mentioned in the book as well. What this does, the DNS is a functional element that converts long numeric addresses for each device or location on a network into a name. So for instance, it's a lot easier to remember nina.org than it is to remember, and I actually looked this up, so this is their IP address, 104.27.180.132. If you had to remember that number to get to nina.org, you wouldn't be able to do it very easily. You would have to look it up every time. So what the DNS does is it converts a name to that IP address. And the same thing happens in Next Generation 911. Each PSAP and potentially even each call station within a PSAP would have its own unique identifier, which could be a very long number. And a DNS would convert that into a smaller code that could be used that would be easier for you to read and remember. So that was part 3, which was Next Generation 911. Now we're going to talk about migration to Next Generation 911 and some of the things that have to be considered as part of that migration. And migration, I've always found it weird to use the word migration. We're not a flock of birds going south for the winter. Migration really just means transition. So we're transitioning from one network, being the E911 network, to another network, which is the Next Gen 911 network. But before we talk about the considerations that have to be taken into account for migrating, we should talk about why Next Generation 911 is important. So there's several different reasons that are listed here. This may not be a complete list, but this is some of the stuff that's mentioned in the book, so I wanted to talk about it here as well. Number one, to keep 911 capability of handling any type of communication. So as mentioned, NextGen 911 can handle any kind of data that the PSAP wishes to receive. Doesn't mean every PSAP has to get every type of data that's possible. The PSAPs, especially in a state like Colorado with a lot of local control, the PSAPs will determine what types of data they want to receive. It could include pictures and video and text. It could include automatic crash notification data. I talked a lot about some of these, so I won't go through the whole list. But in the absence of NextGen 911, over-the-top services have kind of stepped in to provide some of these. So a lot of you are probably familiar with Prepared, which is an over-the-top service, meaning that it runs over the top of the internet. It's not transmitting that data over the 911 network. It's coming over separate from the 911 network. And those are great services, but they are reliant on the public internet to function, meaning if there is ever an internet outage, you will lose those services. And they're also more susceptible to cyber attack and intrusion. So as more of these services come out, you may have to have several of them connected to your PSAP to be able to get all of the types of information that you want to receive. Each one of those services connected to your PSAP is a potential cybersecurity risk. Whereas if everything's going through an EZNet, which has border control functions and is built to those standards, cybersecurity standards, much higher than the public internet, it's a more secure way of delivering that information to the PSAP. Number two, to improve interoperability between 911 systems. So 911 centers aren't the only entities that would benefit from 911 data. I talked about the benefit of crash notification data for outside entities, for an example. This is a better way. So Next Generation 911 gives us a way to share that data, not just from PSAP to PSAP, but with other components of the emergency response system. Number three, to improve interoperability between 911 systems. Generally, it is not possible to transfer calls to a neighboring PSAP if that PSAP is on a different 911 network, for example. Right now, we cannot transfer 911 calls from a 911 line in Colorado to a 911 line in Utah, for example, because we're on two different systems. If both Colorado and Utah were on I3 compliant NG911 systems, then transferring calls would be possible. So by having all 911 networks move to the same IP-based standard network, it improves interoperability between those networks. Number four is to position the 911 networks to be able to handle new technologies more readily in the future. Right now, we have had to reverse engineer basically the E911 network just to handle wireless calls and VoIP calls. In the future, there could be a lot of other sources that 911 calls could come from, like sensors on internet devices, like Google Home Assistants or Amazon Alexas. All of those could be potential sources of 911 calls in the future. And right now, we have no way of getting those 911 calls into a network because the E911 network is simply at its limits of what types of new forms of ingress to the network it can handle. Number five is to improve 911 network flexibility when it comes to conditional routing. So right now, you have calls that are routed to a PSAP based on the location of the call. And if that PSAP is unavailable, it can send it to an alternate PSAP, and that's about it. On NextGen 911 networks, you can say, I want calls to go from this area, I want calls to go to PSAP A during certain days of the week or certain times of day, and other days of the week or certain times of day, I want those calls to go to PSAP B. And you can set that up as a policy in the system, and it will dynamically route those calls based on how you write that policy. So it gives us a lot more flexibility when it comes to conditional routing. You can do things like, I want calls for this park to go to the sheriff's office today, even though normally it would go to the police department's PSAP because there's a big festival going on in the park and the sheriff's office is taking point. So there are lots of potential applications for that type of conditional routing that you can do in Next Generation 911 that you cannot do in an E911 system. To improve, number six is to improve the accuracy of 911 call routing. So routing calls based on the phone number and not the actual location of the caller obviously has some limitations to it. We see it all the time with wireless calls. Next Generation 911 routes the call whenever possible based on the location of the caller. So the call will more likely get to the right PSAP the first time. 7 is to better control the threats to 911 systems from outside actors. Right now, telephone denial of service attacks are a real thing that can happen at any time. They have happened in a few different places in the country where systems have been set up to automatically dial 911 over and over and over and fill up all your phone lines. And there's not a whole lot you can do about it if it happens. There's not really a defense for it. Next Generation 911 has the ability to filter out those types of calls once they're detected. And it also has the ability to implement all types of cybersecurity protections and controls that E911 systems are not able to implement simply because it's a more analog system. And then number 8 is to prevent 911 calls from becoming an analog island in a digital sea. This one really isn't mentioned in the book, but I think it's really important that all telecommunications infrastructure and technology, not just in the United States, not just in Colorado, but in the entire world, is transitioning to digital technology. It's transitioning to IP-based technology because it's cheaper, it's easier to install, it's more interchangeable. You can swap out pieces of equipment very quickly, and it is more interoperable. So you can use one type of equipment, or you can just swap out for a different brand and it'll work exactly the same because it's all based on standards. If 911 does not transition to digital as well, we will become an analog system that has to work within a much bigger system of digital systems. And that causes that creates more opportunity for error. It causes more opportunity for systems to fail. And it ultimately will make 911 less flexible and more expensive to operate because we'll have to use all of this custom technology that nobody else in the entire telecommunications sector is using. So those are some of the main reasons for transitioning to Next Gen 911. But there are different types of considerations that we have to take into account when we talk about how to transition to 911. The first area that's talked about in the book is Next Generation 911 operations. So there's a number of changes to PSAP operations that have already occurred and will continue to occur with the implementation of Next Gen 911 systems and functionality. Some examples of these are managing what types of information and data is available to public safety telecommunicators. Not every PSAP is going to want to get video data from callers, but some of them might want to. Those are decisions that will have to be made by PSAP management. In some states, they're made on more of a statewide level. In Colorado, those are probably going to be made on a PSAP by PSAP basis. So those are decisions that PSAP managers should be thinking about now, and in most cases probably already are. Ensuring critical incident debriefings take into account the impact of visual media. If you do decide to take into your PSAP pictures and video, you have to think about what impact that may have on your call takers. And if there are critical incidents, you have to take into account what that impact means in terms of that critical incident debriefing. The increased use of automation and artificial intelligence. How much automation do we want to use? How much are we comfortable with? Are we comfortable with artificial intelligence helping dispatchers make decisions on how to take 911 calls and dispatch them? Those are very important managerial decisions that have to be made. Frequent and comprehensive updates to initial and ongoing training are necessary. As the technology changes, you can't just throw that at your staff and expect them to understand it. You have to train them on it, and you have to refresh that training as the technology changes. There is a need for careful consideration of what new technology to adopt, when to adopt it, and what to avoid. And again, that is mostly going to be done on a PSAP by PSAP basis, even though some standardization is probably desirable so that every PSAP isn't doing something completely different from all of their neighbors. But it is a decision that's going to be made at the local level. Updating policies to guide personnel on the use of the new technologies. You can train them on it, but if there's no policy in place and they make a mistake, who's at fault? Is the PSAP's at fault at that point. It's not the call taker who didn't do the right thing because they didn't have a policy in place that guided them on how to use that technology appropriately. Ensuring that all available information, not just traditional call data, is used in quality assurance and investigation of incidents. If there's a lot more data available to the call taker other than just what they're hearing on the phone, If it could include automatic crash notification data or location information or a picture that the caller sent during the duration of the call, all of that has to be taken into account if you're doing quality insurance or if you're investigating the outcome of an incident. You can't just take what you're listening to on the phone and say that that is the extent of all of the call data. Another area that we need to talk about when we're talking about transitioning to next generation 911 is management. Management responsibilities are evolving and will continue to do so in the face of new technologies. So all of the decisions that we just talked about in the operations page, those are decisions that will be made by management, and management has to keep up on what these topics are and know that these are things that they have to be considering. Greater interoperability between PSAPs will be possible in next generation 911, which means that there is a greater need to standardize operations and training. If you are taking calls completely different from your neighboring PSAP, but your calls are being transmitted to the neighboring PSAP after you take it through an EIDO, that can cause a lot of confusion. So some standardization is probably necessary in order to make sure that that goes smoothly. There will be a greater dependency between local and state oversight. Greater standardization means that some decisions will have to be made at the state level. I'm not talking about my office necessarily making them, but it could be things that are done through a 911 task force like we have here in Colorado. It could be done through a 911 consortium of local 911 agencies like the CCOA. There are a number of ways that can be done, but there will be a greater dependency between local and state oversight. A larger number of options for operations, such as hosted systems, remote operations, and more specialized positions. All of that is possible in next generation 911, which means more decisions to be made by management that are more complex than before. So management has to keep up with next gen 911 capabilities as well. Another area that has to be considered is interoperability. So interoperability of networks and systems is a challenge, particularly during the migration phase or the transitional phase, because we are in a mix of the legacy E911 network and next generation 911, which means that all of those systems have to work together. Next gen 911 networks have to accommodate both IP-based service providers and legacy service providers. So VoIP companies can send us their calls in IP-based format right now because that's how their systems work. Landline companies, some of them can do it and some of them can't, which means that CenturyLink, for instance, as our 911 system service provider, has to be able to take calls in both formats. They are gearing up to start taking calls in IP format from as many providers as can provide it. But it's going to take a while to get all of those providers transitioned over so that all providers are delivering their calls to the 911 network in IP format. More functions may be hosted on a regional or multi-PSAP basis in the future. You might have a logging system that logs calls not just for your PSAP, but for maybe several other neighboring PSAPs as well. Hosted call handling system, we've already seen some of those used in Colorado, but those will be much easier to implement under next generation 911. So we might see more of those in the future. Hosted mapping systems, etc. And when calls can be transferred or rerouted more easily, there's a greater need for interoperability of radio resources as well. So if you can reroute calls not just to a neighboring PSAP, because that's your alternate PSAP, but you can reroute calls to a PSAP 3 or 4 counties away because there's a major incident that's affecting an entire region of the state. That PSAP 3 or 4 counties away needs to have some way to dispatch those dispatch units for you. So extending the ability of radio, the availability of radio resources is an important consideration as well as next generation 911 becomes more implemented. Automated call data delivery, such as alarm systems and automatic crash notification, means also that systems must be compatible to receive that data. It doesn't do any good for a car to send you 300 points of data about a crash if your system has no way of collecting that data or storing it, for instance. Funding is another consideration under next generation 911. The explosion in communication options made available through IP-based communications has challenged the fee-based structure that is traditionally paid for 911 services. So most of your 911 services are paid for through 911 surcharges, with a little bit being kicked in by county and city budgets. This has increased. The reliance on 911 surcharges has increased over the years, where some 911 centers in Colorado are being paid for almost entirely out of their 911 surcharges. But at the same time, we have devices that don't use phone numbers anymore and don't pay a monthly fee that could potentially access 911 in the future. And that puts the entire funding structure in jeopardy. Examples of these are Wi-Fi only devices. People might get a Wi-Fi only device that can make phone calls over a VoIP network, but doesn't have a monthly subscription or phone number associated with it. So there's not an easy way to assess a surcharge for that user. We already have devices that do annual subscriptions, which makes it difficult to apply a monthly surcharge if you're only paying once a year for that device. Coming soon, we have calls for service from Internet of Things devices. There has been talk for a couple of years now about Amazon Alexa wanting to be able to initiate calls to 911 from the device. If somebody says, "Hey Alexa, I need you to call 911," right now it can't do that, but in the future, if it does that, how is it going to do that? How are we going to bill that person essentially for 911 services if there is no monthly bill that they're receiving? And another problem that we're already seeing is scalable enterprise VoIP systems that have no clear number of lines to charge. Traditionally, there was a number of lines associated with every multi-line telephone system, and we could assess a number of surcharges based on how many lines that system had that were connected to the public switch telephone network. That's no longer how VoIP systems work. They work based on on bandwidth, and you can have any number of lines, outgoing lines, active at any time. So how do you determine how many 911 surcharges to assess on that system service provider? So all of this is occurring at the same time that 911 authorities are being tasked with paying for a very expensive transition of technology and ramping up of services, which is creating a crunch on funding, not just in Colorado, but in the entire country. And governance is a big area as well. So state and federal statutes, regulations, and tariffs that are written for older technologies have to be updated to allow for and take into account newer technologies and realities. These include the collection and eligible uses of 911 funds. Colorado's 911 funds eligibility statute is pretty broad and covers next generation 911, but a lot of states had to update their statute to allow 911 funds to pay for next gen 911 systems. State and local 911 authority has to be revisited. Do the entities that are responsible for implementing 911 have the authority to implement all of the things that come with next generation 911? The definitions and terminology in our laws and in our regulations have to be updated because, as you heard today, there's a lot of new terminology. There's a lot of new acronyms that are related with next generation 911. What we've done in Colorado is we've changed that terminology to be very generic so it can apply to either legacy or next generation 911 systems. But in other states, the terminology they had in their rules were very specific to legacy 911 technology. So they've had to update all of that. Rules need to be put in place concerning access to shared databases. Who owns the data that goes into that database? How does if the logging recorder is shared between multiple PSAPs or even on a network-wide basis, how does the chain of custody work for legal cases? Rules concerning what kinds of devices can access the network have to be established. New privacy protections need to be considered, liability protection, regulatory oversight of advanced services, and governing bodies for broader funding mechanisms. For instance, in Colorado, this year we just passed a bill that creates a it's not next gen 911 specifically, but a 911 services enterprise that can be used to fund systems and services on a statewide basis, as well as providing grants to local agencies. That is an example of us looking at creating a governing body for broader funding mechanisms, not to replace the local funding mechanisms, but to supplement them. And so, wow, 7:30. I did it right on time. This is the last slide. We talked about E911 terminology. We talked about network and switching configurations and transport facilities. We talked about selective routing, E911 selective routers and their features, signaling systems, transmission systems, what Next-Gen 911 is, and we went over some of the Next-Gen 911 terminology. We talked about why Next-Gen 911 is happening, and then we talked about various areas of consideration regarding transition to Next-Gen 911. We are at time, but I don't have anywhere else to go. So if anybody has any questions, I'm happy to stay on and answer those for you. I know I threw a lot at you today. This was probably not a good grouping of topics for one session, but it is what it is. So I hope that once we get this uploaded to the Resource Center website, that you can go back and rewatch it. And maybe if you have questions later, you can reach out to me as well. But does anybody have any questions right now? Did I just baffle you? All right. Well, like I said, this will be uploaded as a video to the Resource Center website, probably within the next couple of weeks or so. In the meantime, if anybody has any questions, or if you have the study guide, which I have laying out right in front of you right now, if you have the study guide and you're going through these sections and you have any questions, I'm happy to try to answer them for you. Just reach out to me at Daryl, daryl.branson@state.co.us. In fact, I think I have it on the next page. Yep, there it is right there. Or any of these other fine people that have taken the lead on organizing these sessions. I'm happy to, any of us will be happy to try to answer these questions for you. Okay, well, if there's nothing else, I will stop the recording and we'll call it an evening. Thank you everybody for attending and hope to see you at a future session.